To realize impedance matching circuits, we can use L and C, lumped components, inductor and capacitor. But at high frequency, such components have parasitic effects. That means an inductor starts to behave more than an inductor, or a capacitor starts to behave more than a capacitor. It might have some inductive effects. An inductor might start to behave as a capacitor at very high frequencies, where the so-called parasitics of that particular component starts to kick in. So to realize such lumped components is often difficult at very high operating frequencies. In that scenarios, it is often useful to realize the reactive impedances that forms the matching circuit using transmission lines instead of lumped elements. So using a section of a particular transmission line to realize either a capacitor or an inductor, that particular section of transmission line is called as a stub. So this particular stub is nothing but a transmission line of a suitable length that is either terminated by an open circuit or a short circuit to realize either a capacitor or an inductor, either a capacitive reactance or an inductive reactance. So depending on the operating frequency, the length of the stub can be determined. What do we mean by that? Let's say we have a short-circuited transmission line of length L stub. We know that the input impedance of this transmission line is a function of the length in terms of the electrical length, and it is given by J Z0 tangent beta L. J Z0 tangent beta L. So it is a reactive impedance having no resistance. It's just J Z0 tangent beta L. And we know that the tangent curves look like this: 0 at 0 degrees and infinity at pi by 2. So if I were to plot it in terms of beta L stub, the tangent beta L is going to have at pi by 2, when beta L equal to pi by 2, it's going to offer infinite impedance, and this is the X in the reactance of the input impedance, and 0 at L stub equal to 0, which is basically a short circuit. We notice that till pi by 2, it is having a positive reactance, which is a nature of an inductor, and beyond pi by 2, till up to a value of pi, it is negative like a capacitor. So to realize an inductor, I can operate a short-circuited stub in this region to realize an inductor. The same short-circuited stub with a longer length, I could use it as a capacitor, making it operating at this somewhere in that range where the reactance is negative. So depending on the choice of the length L stub, we can either realize an inductor or a capacitor. The same works when you're having an open circuit where the input impedance is given as negative J0 cotangent beta L. Let's take a look at what are the range of the lengths for which the open circuit stub behaves as either an inductor or a capacitor. Let's say for an open circuited stub, we know that the input impedance is negative J0 cotangent beta L. As long as the length is less than lambda by 4, this section of transmission line is going to offer a capacitive reactance. And for a length between quarter wavelength and half wavelength, it is going to offer inductive reactance. And this is going to alternate capacitive, and inductive as the length increases beyond. Similarly, a short-circuited transmission line behaves as an inductor for lengths less than a quarter wavelength, and it behaves as a capacitor for lengths between quarter wavelength and half wavelength. Beyond that, it starts to operate as inductor, capacitor, inductive, capacitor. It repeats itself as the length is increased. So if we want to realize a particular inductance or a particular capacitance, I can either choose an open circuited stub or a short circuited stub and choose its length so that this reactance is equal to the reactance that I want to realize. Similarly, this reactance is the reactance that I want to realize. I can choose the length of the stub in such a manner that I am able to realize that inductance or capacitance to finally build the matching circuit that we want to realize. So we are seeing a scenario where how such a stub is usually connected for matching. In essence, we are having a certain load impedance ZL. We want to match that load impedance to, let's say, 50 ohms beyond a certain point. Beyond this point, what we want to see is simply a matched impedance of 50 ohms. So means that we want to transform this ZL in such a manner that when I connect by either a capacitor or an inductor in parallel, in this case we are looking at a parallel stub, by connecting a parallel stub, eventually we want to see the looking in impedance to be 50 ohms. So this particular example, we are looking at a shunt connection of the stub. That means this particular stub is being connected in parallel to the feeding transmission line. Now, the design parameter becomes what is the location where you want to connect that shunt stub and what should be the length of that shunt stub. Those are the two variables that you want to have. To keep it simple, the characteristic impedance of the feed transmission line and the characteristic impedance of the stub is fixed the same. So the two variables are the length of the feeding transmission line LS where we connect the shunt stub, and the second variable is the length of the stub itself. Illustration of the movement of the different impedances in the Smith chart is shown here, where again two possible realizations are possible, two kinds of stubs are possible. Either we can realize an open circuit stub or a shunt circuit stub. In this case, we are going to see an open circuited stub that is being connected in parallel. We start at the certain load impedance that is given to us. Let's say that load impedance is this point in the Smith chart. Finally, at certain point where we connect the shunt stub, we want to hit a 50 ohm impedance. That means when we normalize 50 ohms in the Smith chart, we are right at the center of the Smith chart, which is the bullseye point, the center of the Smith chart, which is the matched load. That is the destination point that we want to achieve. So to determine the LS where we want to really connect this particular stub is, how do we determine that? Is now that we know that this particular stub is being connected in shunt, what we are looking at is looking at the admittance chart, because this particular stub is being connected in parallel. If it were to be connected in series, then we will be looking at the impedance chart. But since in this example we are looking at this being connected in parallel, we are looking at the admittance chart. We need to see that this particular ZL, we know that as we move along the transmission line, we need to move by a distance of LS, that distance LS, so that we hit a particular point in the Smith chart where when we connect this parallel stub, it gets nicely mapped, moves that particular point to 50 ohms. As we move along this transmission line, we know that for every distance LS that we move in the transmission line, we are moving along the reflection coefficient, constant reflection coefficient, which is basically a circle by an angle of 2 beta LS. We are moving by an angle of 2 beta LS in the clockwise direction. So as I move along from the load, right at this point, without the stub connected, I have come to this particular point in the Smith chart, moving by a distance of 2 beta L along the constant reflection coefficient curve. Magnitude of reflection coefficient is constant, just the phase changes by 2 beta L, and we hit this particular point and we stop there. What is so special about that particular point is that point is the constant conductance curve with conductance equal to 1. It's a constant conductance curve with conductance equal to 1. We need to move to that point where the conductance is equal to 1. The normalized conductance is equal to 1, which is this intermediate, represented by this intermediate impedance. So the impedance at this point is basically the line impedance as you move by a distance of Ls from the load impedance. Now all that remains, we have found out what is Ls, because 2 beta Ls is this angle. From there we can figure out what is Ls. What remains to be figured out is the L stub, the length of the stub. We need to figure out the length of the stub, and to do that, again we go back. Since the stub is being connected in parallel, we are moving this impedance point along the constant conductance curve to the center of the Smith chart. So how much of the conductance or how much of the susceptance that this particular stub has to offer can be determined from this particular movement that we want to achieve. Based on that, using this formula, we can figure out what is the length of the stub that is needed to realize that. So an equivalent circuit of the whole scenario is depicted here, where we have two impedances, or rather two admittances, and these two impedances are connected in parallel. We have the load here and the stub here, but the load impedance is what is viewed at a distance of Ls from the load impedance. The G equal to 1 curve is only the choice of the G equal to 1 curve, selecting that particular point here, is one of the two possible choices. There is always, because the G equal to 1 curve has this one full circle, the intersection happens even here. Turns out that you can choose even this point or this point, it doesn't matter. We can either choose this particular point to stop or this particular point to stop to realize the length. It is just that if you choose this point, you're going to have a longer transmission line section where you connect the stub, and the nature of the stub that you realize is going to be a capacitive stub. It is going to be a capacitive stub because the movement of this particular point is in the admittance chart in the clockwise direction. What if we were to stop at this particular point and then we are moving in the counterclockwise direction in the admittance chart? That realization is also possible, and in that realization, the stub that we realize is going to have inductive susceptibility. It's going to be more of an inductor, because the movement of this admittance point in the Smith chart is as if it is, the susceptance is decreasing. It is going in the counterclockwise direction to hit the bullseye point, the matched impedance at the center. So both these realizations are possible, and this illustrates how we can realize using an open circuited stub either a capacitor or an inductor. It is essentially called as distributed element matching. Instead of using lumped components, we are using transmission lines to realize the necessary reactance and or the necessary inductance or the necessary capacitance.